Welcome to this lesson of our study of induction. So we are learning how to write mathematical proofs, and the first concept that we are studying here is what we call mathematical induction. Okay, so we have our first lesson on what we mean by first principle of mathematical induction, and then this lesson is going to talk about strong induction. Okay, so basically both first principle of mathematical induction and strong induction are the same, just that in the strong induction there are some few things that you do differently from the first principle of mathematical induction. So let's go through the idea of strong induction together. So the idea here is that you're supposed to show that your base case, p of 1 or p of 0, depending on where your n is starting from, is true. So when you show that is true, then sometimes you're supposed to show other base cases as well. So you're supposed to show that some other cases, if needed, are true, and show that all these guys, p of 1 and p of 2 and then p of 3 all the way to p of k is true, will imply that p of k plus 1 is also true. So what you're going to do is you're going to show some base cases, and then all of them should be true, and that if all of these guys are true, then if you consider k plus 1, that should be true as well. So the general idea behind strong induction is that the base cases most of the times are more than 1. Okay, so that's what you do. Now let's pick this problem here. So we have an example 1 that says that if n is a natural number, then 12 divides n to the 4th power minus n squared. Now let me write a proof here and start. To prove this, if I say 12 divides n to the 4th minus n squared, or n to the 4th power minus n squared, then it means that I can write per the division algorithm, I can write n to the 4th power minus n squared to be 12 multiplying some integer a, right? So here this integer a is greater than or equal to 0, since we're dealing with natural numbers here. Okay, indeed 0 can be written as 12 multiplying 0. So now the base case, sometimes how do I know that I need multiple base cases? So first, my advice here is that you start with a simple base case, just one of the base cases, and after solving or proving that the first base case is true, you prove that p of k is also true, and then you prove that p of k plus 1 is true. And depending on how you prove p of k plus 1, that is when you decide to come and argue for other base cases as well. Okay, so now let's start with the normal one. The base case is that you're supposed to show if p of 1 is true. P of 1 is such that 1 to the power 4, so wherever you see n, you put that 1 to the power 2, which is equal to 0, is equal to 12 multiplying something. And what do you think should be multiplied? It's equal to 12 multiplying 0, right? So this guy is actually true. So the first approach, or the first thing that is the base case, is saying that this is true. Now the second one is the inductive step. So if you've watched my first video, you know these steps. It's such that, so we now assuming that for n greater than or equal to 1, so when n is starting from 1 all the way to k, so assume for k greater than or equal to 1, so we started, this guy was when n is equal to 1, right? So we're starting with some k which is greater than or equal to 1 is true. This implies that what? It means that if I substitute, or if I sub n with k, it means k to the power 4 minus k squared should be equal to some 12 multiplying a constant. All right, so all these a's will be different from different n value that you pick. Okay, so we assuming this is true. All right, now let's consider something. So that is how I solve my inductive or induction problem. So consider n equals k plus 1. So when n equals k plus 1, let's try to put k plus 1 here and see if you can simplify that into 12 multiplying a, right? Now this will imply that we'll have what? We'll have k plus 1 to the 4th power minus k plus 1 squared. Now I want to rewrite this guy. Okay, so there's a little trick here. I will solve similar problem, and that one I hope you get it. But for this one, let's try to go through it together to make sure that we all understand what I'm going to do here. So we want to write this in such a way that after expanding these guys, I will get some terms that will be multiples of 12. Okay, so I'll get some terms that will be able to be divisible by 12. But then I'm going to use this idea here, right? That k squared, sorry, k to the fourth minus k squared is actually equal to 12a. Now this is true for everything that is less than k. So we are assuming that for k greater than or equal to 1, this is true. So it means all the way to k. I mean n equals k. So since you show that when n equals 1 is true, it means everything that is below k is true. So if I pick maybe k minus 1, it should how do I put this? It should satisfy this condition here. That's the right word to use. That k minus, if I pick n equals k minus 1, then k minus 1 to the fourth minus k minus 1 squared should be 12 multiplying something, right? So anything that is below k is true. That is the condition, the idea here. And this is what brings about the strong induction. You don't just look at only k, but you look at values that are less than k. So here is when n is equal to k. So we've been able to show from 1, the argument is that everything that is less than k also satisfies this condition. All right. So now I want to rewrite this k plus 1 and that guy so that when I expand it, I'm going to get only multiples of 12. Now notice that k plus 1 is the same as k minus 5 plus 6, right? If I add these, I'm going to get k plus 1. The idea is if I sub this 6 here, if I put it inside this, and this guy is less than k, notice that one, so it means it's satisfied this condition I have here. I don't know if you get a point. So anything below k and k itself should be a point that thing to the power 4 minus that thing squared can be rewritten as 12 multiplying a, right? So this is equal to the idea, like I said, is to be able to use the inductive step that we said here, the k, and also be able to rewrite our expansion in terms of only multiples of 12, so that we'll be able to prove it. Then minus k minus 5 plus 6 squared, right? So now k minus 5, clearly we can say that k minus 5 here, so we know k is greater than or equal to 1, so we know that 1 is less than or equal to k minus 5, and it's less than 12 k, sorry. So we can just replace the whole of this as an L and say that this is saying that 1 is less than or equal to L less than or equal to k, right? Where L is this guy, or you can put P there, right? So let me go to a new fresh page and simplify whatever you have there. So we are saying that k plus 1 to the power 4 minus k plus 1 squared is written as some k plus k minus 5 plus 6 to the power 4 minus k minus 5 plus 6 squared, right? So we have these, and what this is trying to tell us is that we can replace the whole of this as L plus 6 4 minus L plus 6 squared. The idea is when I expand this, I'm going to get multiples of 12, except this guy, L, but I know that 1 is less than or equal to L, less than or equal to k, because L is k minus 5. So k minus 5 is less than k. If I have 10, then 10 minus 5 is less than 10, right? So you can argue it that way. Now to expand this, notice that I'm going to use Pascal's triangle here, but if you think you can do it straight away, you can go ahead and do it. So with a Pascal's triangle, you can try to rewrite all the coefficients. So if I have something to the power 0, then I'm going to have coefficient of 1. So let me put it here. If I have something to the power 2 things summing, so if I have a plus b to the power n, and n is 0, I'm going to have only 1, because everything will give me 1. But if n is 1, then I'm going to get a plus b, which means I'm going to get the coefficient to be 1 1. If n is 2, I'm going to get the coefficient to be 2 3 1 2 1. If n is 3, I'm going to have 1 3 3 1. If n is equal to 4, I'm going to have 1 4 6 4 1, right? So these are going to be my coefficients. Notice that this is the powers I'm talking about, right? So now to expand this guy, I'm going to have L to the power 4. So the first one will pick the biggest power. When it picks it, the other one picks power 0, but I will not write that. 6 to the power 0 is going to give me 1. So after doing everything, this is how the expansion is going to look like. I'm just going to write it straight because I gave you how you're going to do it. So this will give you plus, then 6 to the power 1. The coefficient didn't come, so the coefficient here is 4 because the first coefficient is 1, so I didn't write that. 1 multiplying that, and when you keep on doing that, you're going to have 4 multiplying 6, 3 plus 6 multiplying 6 squared. This 6 squared is coming from this guy, okay, and that's 6. The 6 in front is coming from this coefficient here. This 4 is also coming from this guy, okay. So that is how you go. Then L squared, I guess, plus 4. That's the next coefficient. 6 cube L plus 1 multiplying 6 to the power 4. So that's the expansion for the first term. Now the next term is minus the square term. You know how to do that, right? Plus 2 multiplying 6, then L plus 6 squared. So if we had known how to, if you knew how to go about this guy, I'm sure probably I wouldn't have gone through all these, but so this is L to the power 4 plus, if I multiply 4 and 6, I'm going to get 24 L cube plus 6 multiplying 6 squared is the same as, I just want to leave it as a multiple of 12. 36 is a multiple of 12, right? So it's going to be 12 multiplying 3. L squared, these guys are multiplying. Notice that. Plus, 4 times 6 cube, I'm going to write it as 24 multiplying 6 squared, or maybe 36. I think that will be better. 36, oh, so sorry. Let me pick my pen. 36, then L plus 6 to the power 4 is the same as 36 times 36. I mean, it's 6 squared times 6 squared, so I can write it that way. And minus L squared minus 12L minus 36. All right. Now this is going to be equal to, if I pick this guy and that guy, I'm going to have L to the power 4 minus L squared plus 24 L cubed plus 6 multiplying 36 L squared plus 24 multiplying 36 L plus 36 multiplying 36 minus 12L minus 36. So I'm not going to solve any of these. I'm not going to add these guys. So I'm leaving them like that. This guy is 36 here. So notice that we said if you have for n equals k, anything that is below that, okay, anything that is below this guy, anything that is within this, okay, so this inequality here is supposed to be less than that. We know L is k minus 5, so k minus 5 is less than k. So anything that is from all the way from k to all the way to 1 satisfy the idea that that thing, okay, so L is below k, so it means L to the power 4 minus L squared should be written as 12a. We showed that assuming that P of k is true, you go all the way to k is true. So it means by an inductive step, you can rewrite this guy as 12a plus 24 is the same as 12 multiplying 2L cubed plus 36 is the same as 12 multiplying 3. So I'm going to write it as 3 here plus 24 times that is 12 multiplying 2 multiplying 36 L plus 3 multiplying 12 multiplying 3 or something. Okay, so 12 multiplying 3 multiplying 36. I mean 12 out of this, then I can, that guy is just 12L minus 12 multiplying 3 or 3 times 12. So sorry. Okay, I guess there's no that. Okay, so you realize everything here has a 12 in that, right? Every term here has a 12, and that is because we wanted to get that. And that is the reason behind k minus 5 plus 6 that we did. Okay. So actually what you can do in the division problem, if you have a problem that is similar to this, what you can do to know what to do is pick the factors of 12 and look at which one do I have to, subtract from k, that when I expand with whatever argument given, you'll be able to get only multiples of 12, right? So this guy is going to be 12 into a plus 2l cubed plus 6 multiplying 3l squared plus 2 multiplying 36l plus 3 multiplying 36 minus l minus 3. Notice I factored 12 from each one of these terms. So all of these, if I add them, I'm going to get a number, right? I'm going to get an integer which is non-negative. So this guy, k plus 1 to the fourth minus k plus 1 squared, which was L plus 6, fourth minus L plus 6 squared, has been written as 12 multiplying something, let's say P, where here P is actually equal to what? I'm not going to write that. Let me show you. P is equal to all of these guys, everything you have here. So P is equal to everything you have here, right? So 12 multiplying something. That's what I wanted to show, right? I wanted to show that P of k plus 1 is actually this. Now notice that your L was given as what? K minus 5, right? And then we are saying that, so P of k plus 1 is actually satisfying the idea that we can rewrite this as 12 multiplying something, right? Where this P is actually a non-negative integer. So it's true, right? This is true. So we can end here. But notice something. We left some base cases inside that. How do I know that I left some base cases? Okay. So before, I just used only one base case and I proved this. But for it to be mathematically right, you're supposed to argue for other base cases. How do I know this? You're supposed to check this. We know that 1 is less than or equal. We started from counting from 1, right? So 1 is less than or equal to L less than K. That is the argument we use to prove this P of k plus 1, right? This is the argument we use. Now let's put K here. Let's put L is equal to K minus 5, right? Let's put that inside this. Less than or equal to K minus 5, less than K, right? Now looking at this side of the inequality, this is true, right? K minus 5 is actually less than K. That is true. Now we have 1 less than or equal to K minus 5. Is this true or not? Let's go and check something. We started our base case with K greater than or equal to 1, right? Because we chose only 1. We chose the base case n equals 1 to be that. So it means whatever K that we want to get to should be greater than or equal to 1, right? So starting from all the n values greater than or equal to 1 all the way to K. So K is actually greater than or equal to 1. That's where we started. It's true. So the problem is, okay, so K can start from 1, right? So let's go here and check. When K is equal to 1, what happens to this inequality here? When K equals 1, we'll have 1 less than or equal to 1 minus 5, which is not true. This is not true. So it means you're supposed to actually start K from somewhere. That is where you start a base case. You're supposed to start K from somewhere, not K greater than or equal to 1. So to do that, what you choose to do is you solve this. We know that smallest value n is starting from is 1, right? So you solve this equation for L, and then you choose to find your K. So now L is actually K minus 5, so you get K equals 6, right? So it means you're supposed to show the base case, all the base cases from n equals 1, 2, 3, 4, all the way to 6. And then we can start saying that, okay, then the claim is true for K greater than or equal to 6. Okay, this is actually based on the kind of L we use. If we had used something like L minus 4 or maybe L minus 3, K minus 3 rather. If we had used K minus 3 plus 4, notice that this will give you 1, and 3 and 4 are also, this will give you K plus 1, right? 3 and 4 are also factors of 12. I mean, this 4 particular Okay, this is what you should always use. This is actually a factor of 12. But then, when I expand this here, if I use this and expand it with 4, I'm not going to get everything to be a multiple of 12. That's why we didn't use 4. Okay. Now, to look for all these things, we just have to go back and argue with that and start it. So when you're able to use that, then the claim is true. Actually, we are done with the proof. Okay, we've proved this, that this guy is true. For P of k plus 1 is true. So the claim is actually true by mathematical induction. But the base cases that we use were only 1. And k, we said k is greater than or equal to 1. For any k that is greater than or equal to 1, the claim is true. No, we should start with for any k that is greater than or equal to 6. So notice that when n equals 1, we said that one was true. P1 is said that 1 minus 1 to the power 4 minus 1 squared is equal to 0, and this was true. Okay, because 0 is the same as 12 multiplying 0. Now n equals 2, we give P of 2 is said that 2 to the power 4 minus 2 squared, and that is going to give you 12, and 12 is equal to 12 multiplying 1, right? We've been able to write 12 as 12 multiplying something. Here A is that guy 1, so this is true. N equals 3 will give me P of 3, say that 3 to the power 4 minus 3 squared. What is that? That is going to be 72 if I solve this, and the 72 is equal to 12 multiplying 6, and so this is true. N equals 4 all the way to, you have to show all these, before you can actually say that your claim is true. 4 to the power 4, 4 squared, and that is going to give me 4 squared out, 4 squared minus 1, and this guy is going to give me 16 multiplying 4 squared is 16 minus 1 is going to give me 15, and this guy is the same as 4 multiplying 4, 3 multiplying 5, and this 2, 4 multiplying 3 will give me 12, and so that is the same as 12 multiplying 20. This guy multiplying that will give me 20. So 4 to the 4th minus 4 squared has been written as 12 multiplying that, so that is also true. When you do for n equals 5, you realize that P of 5 is the same as saying 5 to the power 4 minus 5 squared, and that's going to give you, if you do it well, you're going to get something like 24 multiplying 25. If you follow this same thing like I did, and this is the same as 12 multiplying 2 multiplying 25, which is 50. Right, 12 multiplying 50. This is also true. Now n equals 6, P of 6 is equal to, decide that 6 to the power 4 minus 6 squared equals, this guy is also going to give you 36 minus 35, and this is the same as 12 multiplying 3 multiplying 35. So these two guys will multiply and give you a value, right? And so we have 12 multiplying something. That is also true. So before we started, we were supposed to actually prove or show all these base cases and say that the claim is true for every k that is greater than or equal to 6. Then if k is greater than or equal to 6, the smallest k we started with was what? The smallest n we started with was actually 1. So it means 1 is less than or equal to L and less than k. Now L is equal to k minus 5, right? So k is starting from 6, greater than or equal to 6. So it means it can start from 6. So when k is 6, you have 6 minus 5, which indeed 1 is less than or equal to this guy, because 1 is less than or equal to 1. The equality holds, right? So that is it. And so the proper proof was supposed to be, before you start with the base case, you start base cases, right? So if after all these, you just start base cases and show for n equals 1, 2, 3, 4, 5, and 6. After showing all these base cases, then you can then go ahead and show the proof, the proper proof, using, so here is supposed to be k greater than or equal to 6, and then you start with all these, right? Everything now is perfect, and then you argue the same argument. You argue that this is true, you show that indeed k plus 1 is true, and that this is where the proof will end. I use only this part to show the other base cases that you needed. I hope this helps. All right, thank you, and don't forget to subscribe to my channel if you have not subscribed. I'm going to solve another example using the same method. I actually have 2 examples more to solve, so try to watch those other videos to understand more about this strong induction. See you.